Hey everyone, today I'm presenting my project on optimizing stream data processing using Apache Flink. The goal was pretty straightforward to improve data processing performance, especially in scenarios with uneven workloads. This was achieved by implementing a dynamic scheduling method known as work stealing. So, what is work stealing? A good way of imagining this would be to consider a set of workers performing some tasks. Some workers might get overloaded while the others sit idle. And instead of these idle workers sitting around, work stealing lets them proactively grab tasks from the overloaded workers. So this dynamically balances the workload, minimizes idle CPU time, and boosts the overall throughput. And for this project, I built a custom scheduler that continuously monitors workloads and dynamically redistributes tasks accordingly. This project is built around two major components. First one is the baseline, which uses standard Flink scheduling and simulates real-world bottlenecks, which gives us a solid reference point to measure work stealing algorithm. And the other one would naturally be the work stealing version, which adds a custom scheduler that scores tasks using a metric. High load tasks are flagged early, and idle workers dynamically pull them from the overloaded ones, helping the system stay balanced and perform better under the skewed overloads. Moving on. Let's quickly walk through how the data flows in the system, but before that, let me give you a brief on the dataset which we're using here. This is the NYC taxi trip data for the last quarter of 2024. It's about 9 GB in size and has about 60 million records. This is stored in a CSV, and once the data arrives as CSV, each record is scored on the load it would create using a metric which is trip miles times the fare value. And based on this score load, the tasks are classified and routed. They're either processed through the standard baseline or the dynamic scheduler, which is the work stealing. And throughout all this process, the performance metrics like runtime, throughput, and resource efficiency are being continuously tracked. Moving on to the system design trade-offs. So these are some of the few key technical decisions that shaped how I built the system. Firstly, I used the static threshold over dynamic threshold to identify the heavy tasks. This made the development easier and gave me consistent behavior during the testing time, and also reduced a lot of complexity in terms of real-time calibration, which would have happened with dynamic threshold. Next, I went with binary partitioning, which is just high load versus low load. It's simple and keeps the coordination overhead low. Multi-level partitioning could have balanced more finely, but it would also slow the things down with extra decision making. And finally, I built the baseline pipeline with deliberate inefficiencies like data shuffling and small pauses, which help create a control environment to show how much better work stealing performs under load. Moving on. And of course, I did face some challenges during my implementation, and one of the early issues I ran into was serialization. Flink couldn't serialize nested classes because of a threading issue with the thread lock. To fix this, I refactored those classes into top level definitions, which worked smoothly with PyFlink serialization. Next, I had to deal with data format issues. PyFlink didn't handle Parquet files reliably, so I converted everything to CSV, which ensured clean ingestion and schema validation. Another big challenge was to track how well the tasks were distributed. To solve that, I built a class called TaskAware Mapper. It's a custom mapper that logs per task and per worker runtime metrics, which made it possible to actually quantify the distribution efficiency during the execution. Lastly, I had to manage data skew. Around 6% of the records had much higher low scores. I used hash-based binary partitioning to spread those evenly and prevent a few workers from getting overloaded. Moving on. Moving ahead, there are three major improvements I'd explore. The first one is adaptive thresholding, where we could dynamically set thresholds based on real data samples instead of using a fixed value. Second one is the multiple level partitioning, which would go beyond the high-low splits and allow for final load distribution. And third, a closed loop control system, which would monitor workloads in real time and automatically adjust distribution logic and thresholds per worker. This would help in reducing the skew even further. To confirm that my system works as I intended, I performed the following tests. Firstly, I validated CSV parsing accuracy and schema integrity for essential fields like trip miles and fare. Then I ensured that the load scores were correctly calculated and the distribution metrics were accurately captured. I ran extensive performance tests with various parallelism levels, specifically 2, 4, and 8, to ensure runtime throughput and CPU usage were as expected. I also carefully analyzed the distribution balance across worker tasks to ensure fairness and efficiency. Despite these improvements, the current implementation has some limitations, some of which we've already covered, like binary partitioning and static threshold. And there's diminishing returns on performance gains if parallelism goes beyond 16 workers. This is due to increasing coordination overhead. My current approach doesn't rapidly adapt to abrupt workload changes. However, it does ensure robust error handling, particularly for malformed records and serialization issues, which helps in maintaining the system stability. For my experimental evaluation, I used NYC taxi trip data. Tests were conducted on an 8-core CPU with 16 GB RAM, matching physical cores with a parallelism of 8. Multiple runs showed consistent performance improvements with greater benefits observed under highly skewed workload scenarios. The results clearly demonstrate the advantage of work stealing. Runtime improved by approximately 7.5%, meaning the system completed processing tasks notably faster. Throughput increased by about 8.4%, processing significantly more records per second. These improvements highlight the effectiveness of dynamic task scheduling, especially in real-life scenarios. Another critical metric is resource efficiency, which is defined as throughput over average CPU usage. This ratio measures how effectively CPU resources are utilized relative to the achieved throughput. The work stealing implementation notably improved resource efficiency by around 11.8%, indicating that dynamic redistribution successfully reduced the ideal CPU cycles and made better overall use of computational resources. Quickly summarizing the initial project goals I set out to achieve, all of which have been successfully completed, like setting up a pipeline with CSV ingestion, implementing dynamic task redistribution, achieving meaningful performance gains compared to the baseline. Finally, these experiments did raise several interesting research questions, like how the performance would improve when scaled to bigger data sets. What's the most effective adaptive algorithm for dynamically setting load thresholds? And would multi-level partitioning significantly outperform binary partitioning in more complex workloads? And how sensitive is the benefit of work stealing to varying degrees of data skew? Thank you and have a good rest of your day.